Hello everyone. So this week we're going to move on from related rates and start looking at some different derivatives of different functions. We'll continue doing this here for the next few weeks. We'll look at some exponential and logarithmic functions and how we take the derivative of those, and then that will lead into how we take the derivative of some trig functions like sine, cosine, and tangent. Today we'll start with exponential functions, and more specifically we actually start with what we call the natural exponential function. So in the first video I will just go through the theory. I'm not going to write it all out for you. I have it here and I'll provide a copy of the note that you can read through as well. So I'll take you through and explain a bit of what is here, and then I'll post a second video where I'll work through some specific examples so you can see how this theory works. First thing we need to define here then today is what is the natural exponential function. We've seen exponential functions before where we can put whatever base value we want here, where x is our exponent. That's the part that makes this an exponential function. For what we call the natural exponential function, our base number is this number e. So what is e? Well, e is this irrational number, kind of like pi, that goes on forever, and e is the number 2.718281 ... and so on and so on. If you look on your calculator, most of your calculators, or possibly I would hope all of your calculators, will have that E button on there. So you'd be able to punch that in and you can see some more of the decimals if you want to look at it. Excuse me. So what is that number E? It's called our natural number, or Euler's number. Euler is a famous mathematician. I know his name doesn't quite look like you pronounce it as Euler, but that's how we say it. And he found this number, E, which is calculated in this way. It's the limit as n approaches infinity of this expression here. And if you want on your calculator, you can actually pause for a second and try a really large value of n. Try 1,000,000 or 10,000,000 or even bigger, depending on what your calculator can handle. Punch that into that expression, and what you should see is you will start to get a number that is very close to this value here. I'll post a video from YouTube that goes through a little bit about this number E and where it comes from and its importance. We actually see it in a lot of different places. So I'll post that video if you're interested to start to take a look a little bit at why this number exists and where it gets used. Like any of our derivatives, we always like to go back to first principles. That's our limits, so we can figure out what the derivative of this function is. So if we use our first principles, our limit definition, here it is. And if we then sub in our function, e to the exponent x, we end up with our limit here. We have e to the exponent x plus h. We can use our exponent laws to pull that apart. We could then common factor the e to the exponent x out, and then all I've done is drop the e to the exponent x out front, and I've left the other part here as the fraction. Now, we don't have a limit technique, at least not in this course yet, to be able to evaluate that limit easily. But what I would suggest is that if we're going to allow h to approach 0, we can at least use our calculators to try and see what is happening here. So if we choose an h value that is close to 0, I've just in my example here chose 0.0001. If you try that number, what you will see is that this fraction here actually gets really close to 1. If you want to pause the video again, you can actually try more and more values. They get smaller and smaller, and what you will see is that this value continues to get closer and closer and closer to 1. In other words, if we allow h to approach 0, at the limit, what we will find is this fraction is actually 1, and the derivative is e to the x. Which gives us a unique scenario here, and that is that if I have the function e to the exponent x, the derivative of that is also e to the exponent x. The derivative is the exact same thing as the function. So if we move on from there, then what does that mean if I have something like, say, e to the exponent 4x? And this is going to be sort of the big idea that we use in the examples in the second video. What we have to realize then is that this is a composition of functions. The inner function is actually 4x. We've replaced x with 4x, so there is our inner function. And our outer function is this exponential function e to the exponent x. So if I sub one function into another function, a composition of functions, then this means that we have to use our chain rule. And when we use the chain rule here, it looks a little bit different than what we did before when we had power type functions where we'd have binomials squared or binomials cubed. But the rule is still the same idea. The idea for chain rule is that we would start by taking the derivative of the outer function. The outer function is this exponential function base e, and from our rule here it says that, well, the derivative is the exact same thing as the original function. So the derivative of the outer function is actually just e to the exponent 4x, the exact same thing as the original function. Now our chain rule says we also have to multiply by the derivative of the inner function. In this case, the inner function is the 4x. So we can apply our normal derivative rules here and say the derivative of 4x is just 4. So we have the derivative of our outer function, the exponential function. That's our new rule, which means that the derivative stays the exact same as the original function. And then we have the derivative of the exponent, which is our inner function, which gives us 4. And then I've just reordered this. Typically we put the exponential function at the end, and I'll move the 4 to the front as the coefficient. In other words, from this sort of simple example here, what we see is that many of our questions will sort of look like this idea here. If I want to take the derivative of the natural exponential function, and we could put any function into the exponent, not just 4x, and you'll see in a second some other examples. So if I have e to the exponent g at x, where g at x could be any other function, then the derivative will be e to the exponent g at x. There's our derivative rule for exponential functions. And then we need to take the derivative of the inner function, and the derivative of the inner function will really just be the derivative of that exponent, so g prime at x. There's our theory, and then in the second video I'll walk you through some examples so you can see exactly how this rule gets applied to some more complicated examples.